All right, you guys, so this is going to be the lecture for section 3.4 in college algebra. 3.4 is about graphing piecewise functions, so a function that's got a few different equations for different domains, and as we get going through, I'll walk you through the process both by hand and on the calculator. So please have your graphing calculator handy. If you don't have it handy now, pause the video, go grab your graphing calculator so that we can do some of that together when we get to that point. So this very first equation, also grab your books because I'm going to be going along the problems that are in the book. Okay, so the first problem in the book says we've got these two equations here. One's linear, one's quadratic, and it's going to reference a graph. Okay, that's what the graph looks like, and I've labeled each of those parts with the equations that are there. They want me to use the correct notation to write them as a single piecewise defined function. So here's how that's going to look. Okay, so we're going to go y equals kind of a big curly bracket there. And then we're going to define each of these parts. So it's going to look like negative 2x plus 10 on a certain domain. It doesn't look like negative 2x plus 10 forever. It looks like negative 2x plus 10 when the x coordinate is between 0 and 3. So we'll go like that. X is between 0 and 3. And the other part of the graph is that x squared plus 9x minus 14, okay? And it looks like that graph when x goes between 3 and 7, okay? So then we would say, because it's less than here, it has to be equal to here. It has to be, one has to be less than or equal to, one has to be less than. So between 3 and 7, and it's including 7 because the dot is actually there. So that would be the correct way to write it as a single piecewise defined function. Okay? And then we're supposed to state the domain of each piece, which we've done right here. This is the domain of each piece. Okay? First part. Part B, state the range of the function. So bottom to top, how far are we going? Well, the y coordinate starts at 0 and works its way all the way up to 10. So our range here, oops, sorry, I misspoke, is between 0 and 10 for y. Sorry, I'm a little rusty at doing this videotaping. Okay, so that's what the range should look like. Sorry about the snafus there. All right, let's move on. So for example 2, evaluate the piecewise defined function by noting the effective domain of each piece between negative 5 and negative 1 and greater than or equal to negative 1 there. Then graph by plotting these points and using your knowledge of basic functions. So negative x minus 2, that's a line, you guys. That has a slope of negative 1, goes through the y-axis at negative 2. But over this interval, we're going to test it. So when we put a negative 5 in, which is in this interval, the opposite of negative 5 is 5, minus 2 is 3. Okay? That's going to be what that one evaluates to. Negative 3, which is again on that interval, the opposite of negative 3 is 3. 3 minus 2 is 1. And if you're following along in the book, they have this chart in there. Put in a negative 1. Now this says strictly less than negative 1, so that's negative 1 is not in that effective domain. It's in this one, greater than or equal to negative 1. So negative 1 plus 1 is 0. The square root of 0 is 0. Times 2 is still 0. Minus that 1 is negative 1. Okay? And 0 plus 1 is 1. The square root of 1 is 1. Times 2 is 2. 2 minus 1 is positive 1. And when you put a 3 in, 3 plus 1 is 4. The square root of 4 is 2. 2 times 2 is 4, and 4 minus 1 is 3. So I've got points that I can plot. Now, one thing that I left out that I think we need to be careful of is negative 1 is not in this domain, but it goes all the way up to negative 1. It gets really close to it without getting there. Like negative 1.01 is in this one, but not in this one. So I need to actually test this one at negative 1, and it needs to approach that one without getting there. So when I put in a negative 1, the opposite of negative 1 is 1, minus 2 is negative 1, minus 5 is, oh, I'm sorry, this is part of the domain. 1 minus 2 is negative 1. And so it actually evaluates to the same thing, which is fortunate in this case, so it will look the same in our graph. So our goal is to graph these 3 points, negative 5, 3, negative 3, 1, negative 1, 1, and connect them as though they were aligned, because we know that's linear. These 3 points, we're going to connect like a square root function, which if you remember, a square root function kind of looks like this, like half of a sideways parabola. And so we're going to plot those points and connect them accordingly. And that's what they say when they say using your knowledge of basic functions. So on the next slide, these were the first 3 points over here. We connected them, negative 1, negative 1. And then we connected the points on this one, and we went from there. So that's what your graph should look like if you do it by hand. I would suggest using graph paper for this, and I'm going to include that in the resources at the beginning of the Google Classroom. So graph the function and state the domain and range. Okay, so for this one, I'm going to just test something out here. What I'm going to show you how to do is I'm going to show you how to do this on your calculator. So if you don't have your calculator out, pause the video, grab your calculator. We're going to walk through how to put this into your calculator as a piecewise function so that you can then generate the table, plot the points from there, and get your graph, okay? So what I expect you guys to do in your y equals is you're going to put this equation with parentheses around it, okay? The comma acts as a division sign, and then you're going to put parentheses around that inequality. We're going to talk about how to do that. We have to do something special on the calculator, and we'll get to that point. This one will be similar, 3 divided by x greater than 6, and I'll walk you through where to get those buttons, okay? So this is what it should look like. In your y1, parenthesis, the opposite, parenthesis, x minus 3 quantity squared plus 12, that was the equation, divided by parenthesis, and then you type in x, and you'll see a greater than symbol. Okay, you guys? If you go to second math, there's a test menu, and you're going to get all of the inequalities that you want to get, okay? And then 0, and then in that same menu, that test menu, you're going to go over to the logic column, and you'll see and or, etc. Choose and then I ran out of room. You guys are then going to put the rest of, after the and, you're going to put x less than or equal to 6. Okay? So over here, this is going to be and x less than or equal to 6. Okay? In the second one, 3 divided by parenthesis x greater than 6. Again, greater than, less than, and all in the test menu, second math. Okay? So that's what your screen should look like. I think we can still have our window be negative 10 to 10, so we're not going to monkey with that for right now. Go to your table, and it gives you some values. Okay? We only defined the first function between 0 and 6, so you're only seeing values between 0 and 6. And the second function was only when we were bigger than 6, so you're only seeing values over here in blue when we're bigger than 6 for x. But that gives you some points you could plot on your graph, and then you could go from there. The other thing you could do is just simply press graph, and your calculator would graph these equations, which is what we're going to see on the next slide. That's what that's going to look like, you guys. Okay? Practice that a little bit. Make sure you can make that happen on your calculator. If not, go back, look through the video again, YouTube it, Google it, do what you need to do to make sure you can feel comfortable putting it in the calculator. Now, since we know how to put it in the calculator, I'm going to expect at this point that you guys have your calculator in front of you and that you're going to go into your y equals and you're going to do what we did on the previous slide. I'll walk you through it, but I'm going to make sure you go to the table and we generate the same values. So, in your y1, 1/2 x plus 6 divided by x greater than or equal to 0 and x less than or equal to 4. In your y2, the opposite of the absolute value of x minus 6, absolute values in your math menu over one column to numbers, plus 10 divided by x greater than 4 and x less than or equal to 9. Okay? And when you guys do that, take a minute to put that into your calculator, and then let's go to the table and see what you guys get. Okay, give me 1 sec, I'm just updating here. 1, go to my table. So when I put in a 0, I'm getting a 6. You guys should get the same values in your calculator. When I put in a 2, I get a 5. When I put in a 4, I get a 4, okay? Because the 0, 2, and 4 all fall in this category, so I'm just taking half a 0 plus 6, half a 2 plus 6, and half a 4 plus 6. All right, give me 1 second, you guys. Okay, I had something typed in my calculator wrong. Give me 1 second. All right, so here's what you should get. At 2, half of 2 plus 6 is 7. Half of 4 plus 6 is 8. When you put in a 6, an 8, and a 9, we're dealing with the second equation, so that should be in a different column. Okay, and so when I put in a 6, I'm getting a 10. Okay, 6 minus 6 is 0, plus 10 is 10. When I put in an 8, I'm getting an 8. 8 minus 6 is 2, negative 2 plus 10 is 8. And when I put in a 9, I'm getting a 7. So 9 minus 6 is 3, negative 3 plus 10 is 7. So you should be able to put this stuff in your y1 and your y2. You should be able to go to your table and generate that same graph that we have. And then from there, we should be able to graph it. And we're going to talk about domain and range from the graph, okay? So from the graph, our domain starts at 0. It's included right here, and it goes all the way to 9. So my domain looks like this, okay? My range, on the other hand, is a little disjointed. I start 1, 2, 3, I'm 4 up here. So I go 4, 5, and 6. Okay, and then I also go from 7 to 10. Okay, in interval notation, you guys, this one looks like, and this one goes from 4 to 6, and then again from 7 to 10. There's a little bit of break there between the 6 and the 7. Okay, and we should be able to read that from the graph. Okay, one more time. Let's put this on your calculator. So if you don't have your calculator out, grab your calculator, pause the video for a second. Okay, I'm just changing to new equations in my calculator. Okay, and so x squared minus 4 divided by x minus 2. Use the alpha y equals fraction bar if you can. If not, make sure you have parentheses around the x squared minus 4 and the x minus 2. Divided by x not equal to 2. It's in the same test menu, the not equals to, you guys. And then you put in a 1 divided by x equals 2. And we're going to see what this looks like. Okay, so if you go to your table, you should be able to generate the same points that I generated. Okay, when you put in a negative 4, you should get a negative 2. Okay, a negative 2 should generate you a 0. A 0 should generate you a 2. A 2, now that's going to be for this one. A 2 is going to give you a 1 because that's when x equals 2. A 4 will give you a 6, and a 6 will give you an 8, okay? Now, one thing I want to show here algebraically is what's happening. If you look at that x squared minus 4, that factors to x minus 2 and x plus 2. And we have an x minus 2 in the bottom, okay? Those, for the most part, divide out. So my graph should look a lot like the line y equals x plus 2, a slope of 1, an intercept of 2. But I know that x can't equal 2 because it makes the bottom 0, so there's going to be a hole there. So for this particular graph, if I put a 2 into this one, if I canceled the things out, I would get a 4. But at 2, 4, there's a hole because 2 is evaluating to 1 down here. There's a hole up here, okay? So I would plot those other points, connect them like there was a line, but put a little hole at 2, 4, okay? Otherwise, you generated the rest of the points on your calculator, all right? So there we go. You'll notice again right here, at 1, it evaluates to 1, okay? But at 2, it evaluates to 1, but at 2, 4, there should be a hole here. The calculator doesn't do a very good job of that. It won't ever show the hole, but you have to recognize that there really is a hole. If this were on a homework or a test, you should have a hole there, okay? All right, so now I'm going to give you a piecewise defined function, and I want you to come up with the equation. Okay, well, it looks like I've got a line. We should be able to find the equation of a line. And then I've also got a parabola, okay? So we're going to go like so. We're going to start with a line because I think we can do a pretty good job with that one. If I pick a point like the y-intercept here at -1, to get to another point I have to go up 2 and over 1, which means my slope is 2. So a slope of 2 and a y-intercept at -1, the blue line looks like that equation. But the domain for it goes from -2 to 1. So we need to say that we're going to restrict x between -2 and 1, okay? Now, I'm going to work off on the side here just for a second. I hope you can see everything that I'm working on. This parabola is a little bit different, okay? The vertex for this is at 3, 5, okay? So I know I've shifted to the right 3, and I've moved it up 5. What I don't know is whether I flipped it over an axis or I've stretched it or shrunk it at all. So I gotta calculate what that A is. And I can do that by picking a point that's on there and then solving. So that point 1, 1 is on that graph. So I'm gonna put a 1 in for y. And I'm gonna put a 1 in for x. And I'm gonna just solve for A at this point, you guys, and see what we get. So 1 minus 3 is -2, squared is 4. I'm going to subtract 5. I'm going to divide by 4. So I know A is -1. That gives me the equation of my parabola. So it's going to be the opposite. That's your A. That's that -1. X minus 3 quantity squared plus 5. And it looks like that continues on forever. So that's going to be true when x is greater than or equal to 1. So that's what the piecewise function for that one is going to look like. We had a little bit of extra work to do over here because we had to determine what our A was. Other than that, I think we were pretty solid. Okay? Now let's take a look at some word problems. Follow along in the book. It's probably going to be easier to read on the book than it is on the screen, but we'll work it out together. Okay? I'm going to grab my book while we do this so that I can follow along with you guys. So it says, for the first half of the 20th century, per capita spending on police protection can be modeled by S of t equals 0.54 t plus 12, where S of t represents spending in dollars per person on police protection in the year 1900, which corresponds to 0, for the first half of the century. So for year 0 to year 50, we're only going halfway through. After 1950, perhaps due to the growth of American cities, this spending greatly increases. So now S of t equals 3.65t. The slope is quite a bit bigger, minus 144. Write these as a piecewise defined function. We'll call it S of t. State the domain for each piece, then graph the function according to its model. And then how much was spent per capita in 2000, 2010, and 2014. Okay, well this isn't as bad as it sounds. It's a great big word problem, and I know we get scared about word problems sometimes, but they've given us the two equations, here and here. We just need to figure out the domain when we write the pieces. Okay? Well, one of them tells us this in the first half century, so that goes from year 0 to year 50. And the second one says after 1950. Well, that's going to be when x is greater than 50. So on the next slide, I'm going to give you that piecewise function. Okay? So there's the first equation, 0.554t plus 12, but that only occurs between 0 and 50. Year 0 is 1900, year 50 is 1950. And the second equation they gave us occurs when t is greater than 50, anything past 1950. Okay? Now, I would ask that you graph this on your calculator, you guys. So take a second, pause the video if you need to. You're going to put this into y1 divided by x greater than or equal to 0 and x less than or equal to 50. And in y2, you're going to put this equation divided by x greater than 50. Okay? Before you press graph, think about your window. All right? So your window has to start at 0 for x. And it has to go greater than 50. And as a matter of fact, if you think back to the previous slide, they were asking us to predict 2014. So we need to go out to 150 maybe, 0 to 150. That would be fine. And then for y, when you do put a 0 in here, you start at 12. So I could start y minimum at 0. But what happens when I start putting 50 in, you know? I start getting a lot bigger numbers. So you got to think how high you want to go with that. If you look at my graph here, I'm going to have to go all the way up to 272 based upon what we've got. So I would go from 0 to 300 for your y's. And then press graph. You should get a model that looks like this. All three of these graphs are exactly the same, you guys. The only difference in each one was what I put in for trace, because we were supposed to predict the year 2000. So I pressed graph, I pressed trace, and I put in 100 because 2000 is 100 years past 1990. Okay? And it predicted $221 per person. Okay? In 2010, I put 110 into trace, and it said 257.5. In 2014, I put a 114 into trace, 272.1. Okay, so our calculator can do a lot of the work there. Example 8. In 2011, the first class postage rate for large envelopes sent through the U.S. was 88 cents for the first ounce, then additional 20 cents per ounce thereafter, up to 13 ounces. So think about if you were to graph this, we're only going to go up to 13 for x. Graph the function and state the domain and range. Use the graph to state the cost of mailing a report weighing 7.5 ounces, 8 ounces, and 8.1 ounces in a large envelope. So take a look at example 8 in the book, if you will. Okay, your graph is going to look a lot like this one. Okay, they've labeled it really well in the book. This is representing the weight, 0 all the way out to 13 ounces, certainly, because that's as heavy as we're going to go. And then the cost, well, it started at 88 cents, but every time you added 20 cents, or added in, how much did we add here? Every time you added an ounce, it added 20 cents. So this, for the first ounce, 0 to 1, this is 88 cents. So if it was half an ounce, 88 cents. If it was 0.9 ounces, 88 cents. If it was 0.99 ounces, 88 cents. This is what's called a step function because it looks like we're walking steps up. If, as soon as I switch to 1 ounce or more, then I jump up 20 cents. Now I'm at $1.08. Okay, so if I'm at 1.2 ounces or 1.8 ounces, $1.08. Okay, and so you can follow that along all the way through. So for part A, it asks the cost of mailing 7.5 ounces. 1, 2, 3, 4, 5, 6, 7.5 moves you up to that spot. Knowing that you started at 88, you can count up 20 cents from there and find out that you're at 228 cents, which is $2.28. Okay? B, the cost of mailing 8 ounces. Okay? 8 ounces is in the same spot, right? It's still that $2.28. We have to get more than 8 to jump up to the next amount. The cost of mailing 8.1 ounces. Now I've gone above that. I have to go 20 cents more. Now it's $2.48. And we've gotten to that next level. Okay? So I hope this helps. If you're stuck on any of it, feel free to go onto YouTube and follow other videos. Go to Google, email me, whatever you need to do to get some help. There's your assignments, you guys. I think we're going to go 5 through 35, the odds on this one. I'm going to change it a little bit. So 5 to 35, the odds. I'll change that on the Google Classroom as well. Okay? All right, have a good one. Until tomorrow.